everybody, and welcome to exercise 1 on page 59. Let's take a minute to read through this exercise together. So let T be a linear transformation that takes us from the set of 2 by 2 matrices to some vector space V, and U be a second linear transformation that takes us from V to P1 of R. Okay, and they don't tell us anything about V other than the fact that it's some unknown two-dimensional vector space. That's going to turn out to not be so important in our problem. Okay, and the next piece of information that they give us is matrices, okay, for both of these transformations. So the matrix of T and U look like that and that respectively. And there's some bases running around here. So alpha is the standard ordered basis for the set of 2 by 2 matrices. Beta is some unknown basis for V. It's going to turn out to not matter. Okay, and then finally gamma, that's going to be a basis for P1 of R. Okay, so with all of that information, what they would like is us to find a formula for the transformation UT here. Okay, so this is another one of those problems where we're kind of being asked to go backwards. Instead of calculating a matrix, they're giving us a matrix and asking us to figure out what the formula for the transformation is. Okay, well, how do we do this? Well, here's one way to think about it. The next best thing to finding a formula for this transformation UT is to find a matrix for the transformation UT. So let's start by seeing if we can find the matrix of UT. And there, Theorem 2.11 can help us because we already know what the matrices for U and T separately are. Okay, so we'll start by making the observation that by Theorem 2.11, we know that the matrix for UT, taking us from alpha to gamma coordinates, is going to be the product of the matrix of U, which we can see is 1, -1, 2, 4 from above, and the matrix of T, 1, 2, 0, -3, -2, 1, 1, and -1. Okay, and so you can multiply those two matrices, and if you do that, you're going to get, I'll let you check me on this, 3, 1, -1, -2, and then -6, 8, 4, and -10. Okay, so there's a matrix for UT. It's not a formula, but it's a step in the right direction. Okay, so now the question is, how do we go from this matrix for UT to a formula for UT? Well, remember what a matrix tells us again. Okay, a matrix is a way of taking coordinates to coordinates, basically. Okay, so let's make an observation here. If we take this matrix for UT that we just came up with, 3, 1, -1, -2, and multiply it by a coordinate vector, A, B, C, D, what's going to come out is another coordinate vector. Okay, so if you do this multiplication, and again, I'm going to ask you just to check me on this. Okay, we're just doing ordinary matrix multiplication here to get this. 3a plus b minus c minus 2d, and then let's see, -6a plus 8b plus 4c minus 10d. Okay, and again, this comes down to coordinates. So what we're looking at over here would be coordinates relative to our domain. So these are alpha coordinates. And what's coming out are gamma coordinates. That's really just the definition of what the matrix of a transformation does. Okay, so those two coordinates tell us how to build an input vector and an output vector. So let's start with the coordinates over here, A, B, C, and D. What was the basis alpha? We can scroll up and see. Okay, so alpha was the standard ordered basis for M2 by 2 of R. Okay, and the standard ordered basis for the 2 by 2 matrices looked like, now let's just write this out. 0, 0, 0, 1. Okay, so the matrices in the standard ordered basis would be these four things. Okay, our calculation up here, or what we wrote down, tells us that the coordinates that we want are A, B, C, and D, so we put those in front of those one at a time, and forming that linear combination gives us the input. Okay, think of that as the input that's going to go into our function, kind of looking back at the top of the page here again, ut. All right, and then what we're looking at over here are going to be the coordinates for the basis that goes with our outputs. And so now we need to focus on gamma. Okay, and in the problem they told us that gamma is 1 plus x and 1 minus x, and so we're going to interpret these two numbers as being coordinates on those basis vectors. Okay, I'm going to go ahead and write those down. So 3a plus b minus c minus 2d times the first one. Let's see, I need to peek 1 plus x plus negative 6a plus 8b plus 4c minus 10d is going to go times 1 minus x. And I'm going to postpone that calculation. We could add those together and simplify it, and what that is would be our output. Whoops. Okay, so we have everything that we need now to write down a formula for ut. So ut is going to take our input, which we calculated up here to be the matrix A, B, C, D, and our output is just going to be exactly what we wrote here. Okay, so I'm just going to recopy that. 3a plus b minus c minus 2d times 1 plus x plus negative 6a plus 8b plus 4c minus 10d times 1 minus x. And we might simplify this. Okay, I'm going to leave the algebra to you, but you could actually distribute all of this out and collect like terms, and what you should come up with is this. Okay, we'll put all the constant terms together. Okay, and then put all the x terms together. And again, I'm leaving the algebra for you here. Okay, it really is just a matter of multiplying things out and collecting like terms to get this last line here. Okay, and there's our formula. So we've shown how to take an arbitrary input, a 2 by 2 matrix, and then shown what our output is. That's what we mean when we say a formula for a linear transformation.